let's look at the first example. So in this example, we have a slender bar represented by AB, and this bar has a mass of M, length L, and we are told that it's released from rest in the position shown. Right? In this position, it's creating an angle of 60 degrees with the horizontal plane or the floor, and we are asked to determine the acceleration of end A. How does this point accelerate? Reaction at A, what are the reaction forces, or what is the reaction force at A, and the angular acceleration of the bar immediately after release. Now we're told that we can assume that the horizontal plane is frictionless, so no need to be worried about friction. Now, slender bar, you remember when we were talking about mass moment of inertia, we said a slender bar is a type of bar that we can safely assume that the width is very small compared to its length. So we can safely ignore whatever the width of the bar is, and we are not given the width here, and that's why. Let me see. Okay, so we're going to follow the steps that we introduced, right? We're going to start looking at the kinematics and try to find the acceleration of the mass, center of this mass. So let me put, well, it's a uniform bar, has length L, so the center of gravity would be exactly in the center at point, I'll call it point G. Now to study the kinematics and find the acceleration of center of mass, I need to decide where to put my frame and which body or part of system I'm going to attach that frame to. So I'll put my frame, pretty straightforward, on point A and attach it to the bar. Point B, on point A, attached to the bar. So that would be X, this would be Y. And I'll study point G. I want to find what is the acceleration of point G. So I'll use this frame and say AG is equal to AA plus A relative plus alpha cross R plus 2 omega cross V relative plus omega cross R. Now the frame is attached to the bar. Point G, center of gravity or center of mass for this bar, is also part of the bar, obviously. So there is no relative motion between the frame and the center of mass. They're all part of the same rigid body. They both are part of the same rigid body. So whatever is whatever relative term I have becomes zero, because there is no relative velocity and there is no relative acceleration between point G and the frame. Now, another thing is that I'm told that I have to find the angular acceleration of the bar or analyze this system immediately after release. Remember when we were talking about kinematics of particles? I said whenever we are dealing with such a situation that we are studying the system or a particle or rigid body, we are doing some kinematic analysis, and we are told that we have to do it immediately after release. This means that we have acceleration, but we don't have velocity, because acceleration did not have enough time to create velocity, right? We give acceleration to a system, given enough time, acceleration creates velocity. Now, if there is no time, immediately after applying the acceleration, which is what's happening here, once we release this, the gravity starts applying some acceleration on this rigid body, right? Well, it was applying before, but now you can see the effect of acceleration of gravity on the bar. It starts falling, but there is not enough time for acceleration to create velocity. So there is no velocity at that specific moment. So we can safely assume that omega is also zero. So this term is gone. Now, what is left is, well, AA, the acceleration of point A, and point A is this point on the bar. When the bar starts falling, right, we have some probably rotation in this direction, and this point starts sliding to the left. So we know the direction of this acceleration. Whatever acceleration this point has, it's in this direction to the left. We don't know its magnitude. So I will just put AA as, let me put it a little further this way so I have some room. It's equal to minus AA I, right, in I direction, or negative I direction. I can also draw the vector just for the sake of completeness. This is the vector. Now, the second term is alpha cross R. Alpha cross R has the magnitude of R alpha, and what is R is the distance between the origin of the local coordinate frame and the point we're studying, and that distance, well, this point is exactly in the middle of the bar, so this distance is L over 2. So L over 2 alpha. Now, I'm going to assume that direction, the direction of alpha is in this direction, which is most probably true. I don't want to put alpha AB, it's just alpha. And let's find the direction. We know the magnitude, let's find the direction. It's a vector. The direction, let's say, I plot it here, draw it here, point A to point G. If this is point A, this is point G, this means that my alpha R is in this direction, since alpha is clockwise. So let me do it this way. And that would be alpha. That was my assumption. And this is perpendicular. So knowing that, this means this, if I put the horizontal line there, this means this angle is 30 degrees, since I know the angle that ball creates with the horizontal surface. This becomes cosine 30i minus sine 30j. And that's pretty much it. So AG, which I was looking for, I put I terms and J terms together, so that'll become minus AA plus L over 2 alpha cosine 30 I minus L over 2 alpha sine 30j. So that's the acceleration of center of gravity. That's what I was looking for. Now, next, I'll draw the free body diagram. So let me do that part. Try to put some good estimate of free body diagram. Let's do it this way. All right. So there you go. This is point B, this is point A, and this is G. Put it somewhere right there. And let me just make a copy of this before I start messing around. Alright. Apparently I copied this, so I don't need so the left one would be my free body diagram. I'm going to use it for my free body diagram. The right one, I'll use it for my kinetic diagram. Forces, well, I have gravity, the effect of weight, so mg is exactly on the center of mass, center of gravity, mg. I should put reaction forces on A. Well, usually I put two, one in y and one in x direction, but in this case I'm told that there is no friction. So when this bar, this point A, is sliding to the left, there is nothing resisting that motion. So there is no reaction from on x axis, I would say, at point A. So there's only one upward from the floor or the ground to point A. I'll call that, let's call it FA. There is no x, no y, so I'll go with FA. That's it. That's my free body diagram. Looking at my kinetic diagram, well, I have let's see, I have, well, I'm going to put my acceleration terms or MA terms. I'll separate them, MA gx and MA gy, since I know each component. So I'll call this MA gx. I call this one MA gy. And I also have a moment. Well, mass, moment of inertia around center of gravity times alpha. And that's pretty much it. All right. So I have to write those three equations, right? Those well, two equations for forces, one in x and one in y direction, and another equation for moments. I have to decide about which point I want to take my moments. Well, I'm going to go for point A since I want to kind of get rid of reaction force as an unknown. If I take moments at point A, this disappears. So I have one less unknown in that equation. And that's what I'm going to do. And I'm going to use the first equation for moment since I know the acceleration of the center of gravity. I would say acceleration of mass moment of inertia about center of gravity times alpha plus mag d, right? This is a vector, and ma, I'll take the positive direction as the direction of the motion since I can guess that. Now, well, from the left side, on the left side from free body diagram, moment about this angle is 60 degrees, right? About point A, well, FA is gone. This is L over 2. So mg, the component of mg, well, mg, the moment it creates about point A would be mg L over 2 cosine 60 degrees, this length. That would be mg, mg L over 2 cosine 60 degrees is equal to the right side, well, mass moment of inertia about center of gravity for a slender bar, length L, mass M. We found it when we were talking about mass moment of inertia, 1 over 12 ml squared. Alpha is alpha plus mass times L. Let me just move it down here so there's no room. Plus MAGX, component X, let's go there, here, whatever this component is, multiplied by the distance it has from point A. That distance would be this distance. Since this is 60 degrees and this is L over 2, this distance would be L over 2 sine 60 degrees. That would be L over 2 sine 60 degrees, and that is positive since it creates a moment in clockwise direction. The next term would be the y component, mgy, times, this time L over 2 cosine 60 degrees, since that's the distance I'm looking for, this distance. And it's negative because it creates a moment opposite the direction that I assume to be my positive direction. Now, move things around. We can write it as 1 over 4g is equal to 1 over 12. It would be 1 over 12 L alpha plus square root of 3 over 2 a gx, right? And minus 1 over 4 a gy. Now we can replace a gx. A gx is this term, minus aa plus L over 2 alpha cosine 30 degrees, and a gy with this term, minus L over 2 alpha sine 30 degrees. You do that, and let me just write that step. and make some simplifications. 3 square root of 3 AA. That's what we get. I move things around a little bit and factored out L alpha. So 3 square root of 3 over 2 cosine 30 degrees plus 3 over 2 sine 30 degrees times L alpha minus 3g. Now from there you can find AA, acceleration of point A. You can write it in this term, in this form, but you'll get one equation: 7698 L alpha minus 0.5773 g. This would be your first equation. Right? The equation you get from taking moments about point A. It's a relationship between A, L, alpha, and G. Now, let's find the forces about in x direction. In x direction, well, we have nothing in free body diagram. We only have this component in x direction, which means that this component is 0. Right? Since there's nothing on the left to be equal to this, gives us just 0. So let me just put it there. Go to the next page. Summation of forces in x direction is equal to MAGX. Now from there, well, on rigid body diagram, there is no x term. M times minus AA plus L over 2 alpha cosine 30 degrees. And from there you can actually find AA. AA is L over 2 alpha cosine 30 degrees, which means it becomes 0.433 L alpha. And this is going to be your second equation. Now, let's see what happened. I found AA as a function of L alpha. Right? I can take that, put it into the equation I found before. There you go. I can put AA here. Now I'm going to get an equation which is going to be based on alpha. Right? L is just a constant, G is just a constant. So I'm going to have 0.433 L alpha is equal to this side. And from there I can find alpha. And once I know alpha, I can plug it in to this equation and find AA. So if I do that, I'll get both of those values. Oops, not the right color. So I basically found alpha first. So let me put alpha here. Alpha becomes 1.714 G over L, and AA becomes 0.742 G. These are two things I was asked to find: alpha and AG. Let me just actually, it's better to present them with different colors since these are what the problem was asking for: alpha and AA. The last thing the problem was asking for was the reaction force. Well, to find that, I'll just write the equation in y direction. Fy is equal to mgy. From there, I'll get minus mg plus fa from free body diagram. And on the right side, I get magy. From there, I'll get fa is equal to mg minus L over 2 alpha sine 30 degrees. I know alpha now, right? Alpha is known. I can plug it here, and as a result, I can find fa. From there, this gives me fa as 0.5715 mg. And that would be the reaction force. So I found all three things that the problem was asking for, following those steps.